Okay, this is on lesson 6.6, numerical integration. So we need to use numerical integration in two cases. When number one, you can't find the antiderivative. There are cases that we really have no tool to find the antiderivative. Then you'll use numerical integration to estimate it, right? Or you can't find the area using any geometric means, like it's not a geometrical shape. It's not a triangle. It's not a semicircle. So when these two things can't happen for you, then we use numerical integration to estimate the area, right? So we have some rectangle rules that helped us before. We have LRAM, RM, and MRAM. This N tells me the number of rectangles under the curve that you're using to estimate. And then the width of your rectangles is defined by your interval actually, B minus A, over the number of rectangles that you have. So if you have, a length of 3 and you want 6 rectangles, then each of the rectangle will be a width of 1/2, right? So this is a typical formula for us. And then we started looking at something called trapezoids, right? Because rectangles aren't enough to really help us. Rectangles, you typically have an over or underestimate. Even if the MRAM, half of it's over, half of it's under, and it's not exactly half sometimes depending on the curvature of your graph. So we then look at trapezoids, right? So trapezoid rule looks something like this, where we have a typical function like so, and instead of drawing rectangles under, we are going to draw a trapezoid. We draw our line like this, right? And then we use trapezoids. We use our lines like so to really try to get under the curve as much as possible, right? And you're still sometimes over, still sometimes under, but you are a lot closer to it than you were before, okay? And what is really important to see is you have to turn your head sideways to look at these trapezoids and know that, hey, for the first trapezoid, this is your base 1, this is your base 2. Then for the next trapezoid, this is your base 1 and base 2. Base 1, base 2, base 1, base 2, base 1, base 2, base 1, base 2, base 1, base 2. So notice that all the bases in between are used twice, right? Because of the way trapezoid works. And then the first base and the second base are only used once. So that's why in your formula, notice that the first y value is single, and the last y value is single, and everything else in between is doubled, right? So that's how the formula came about. And then your formula for a trapezoid was base 1 plus base 2 times height divided by 2. Well, height is this distance right here, which is now what we call width, right? Width is b minus a over n. We got divided by 2. That's where the b minus a over 2n comes about. So everything in this formula makes sense. There's a reason for everything in the formula. Another way to look at trapezoid is the average between LRAM and RM. So you would think that that's MRAM, but no. Trapezoid is the actual average between LRAM and RM, okay? And then someone named Simpson found something even better. Simpson says, there's actually a weighted average that you can do by taking 2 midpoints and 1 trapezoid, and then multiplying divided by 3, you will actually get an even better estimate. And so again, we know this because we were able to test this out with actual integrals. And so because it actually works with actual integrals and actual curves that we know, then we know that it works for curves that we don't have the exact answer to. All right. So Simpson's is actually the most accurate estimation, and then trapezoids, and then MRAM and LRAM and RM kind of go hand in hand, right? So this is a long way of Simpson. Simpson says b minus a over 6n because of the mix of trapezoid and midpoints in there. And then the way you do this is all the midpoints, you got to multiply by 4s, and then all the actual values in between, you got to multiply by 2. Kind of like the trapezoid up here, except now we added in these midpoints because we have MRAM in our Simpson's rule here. Okay. All right. So given a problem that looks like our example here, we are going to see how to do all 5 of these using the t-table given to us. Now, because we need some midpoints, you have to strategically plan this, meaning that you can't call each of these values x0, x1, x2, x3. You have to skip every other one in order to create your midpoint. So this will be our x0, this is x1, x2, x3, x4, x5. What this tells me is now my n equals 5. I have 5 rectangles, 5 trapezoids, 5 intervals basically. And then if you need to, my interval here is 2 to 5. So my width is 5 minus 2 divided by 5, which is 3 over 5, which gives me 0.6. And you should see the distance between each of these is 0.6. So our interval, our width of the rectangles are uniform. They're exactly the same. Okay? All right, so let's take a look at a few things we do know already. So we start with LRAM. LRAM, we have a width of 0.6, and LRAM says we use every y value except the last one. So which y values am I looking at? I'm looking at first, second, third, fourth, fifth, right? All 5 of those that I just highlighted. So 12.1, 8.4, 5.8, 5.9, 7.6, right? I get 0.6. All right, so let's see, 12.1, 8.4, 5.8, 5.9, 7.6, 39.8, and times 0.6, I get 23.88. Okay, so then for RRAM, remember, we don't want to take the first one. We want to take all the y values starting the second and all the way to the last one here. So RRAM will be 0.6 times 8.4, 5.8 plus 5.9 plus 7.6 plus 11.8. All right. So again, if you had written all of it out, you could have used your 39.8, subtract the first value, and add the last one to get 39.5, and then multiply by 0.6, I get 23.7 as my RRAM estimation. Okay. All right, and then now we look at MRAM. So MRAM uses all the midpoint values. So all the midpoint height values are here. These are the midpoint height values. So you get same width, 0.6, you get 10.4, 6.2, 5.3, 6.4, and 9. All right, so 10.4, 6.2, 5.3, 6.4, 9. I get 37.3 times 0.6. I get 22.38. So that's my estimation using MRAM. Okay. All right, so now trapezoidal rule says we are going to follow the formula. Now I know I can go ahead and take the average of LRAM and RRAM, but I don't want us to do that. I want us to use that as a checkpoint for ourselves later. So let's go ahead and use the actual formula for trapezoid to see how it works, right? So the formula for trapezoid is B minus A over 2n times the first y value, so 12.1, double the next, and then double the next, and then double the next, and then double that, and then the last one don't, right? So then you get your outside value to be 0.3, because think about it, it is really essentially our height divided by 2. So our width was 0.6 divided by 2 is 0.3. Makes sense. And then the inside is going to be a little bit bigger because we're doubling a lot of the values. So I am at 2 times 5.8 plus 2 times 5.9 plus 2 times 7.6 plus 11.8. Oops, 0.8. I get 79.3 times 0.3. That gives me 23.79. And let's check. Take our LRAM and RRAM, 23.88 plus 23.7, and divide it by 2, we get 23.79. So we know for sure our trapezoid is correct. Okay. All right. Last one. We're going to do Simpsons. So Simpsons now requires everything, including the including the midpoint values, right? So Simpsons, S sub 5 equals B minus A over 6n. Okay, first value 12.1, and then you multiply by 4. The midpoint get multiplied by 4. So 4 times 10.4, 2 times 8.4, 4 times 6.2, 2 times 5.8, 4 times 5.3, 2 times 5.9, 4 times 6.4, 2 times 7.6, 4 times 9.0, and 11.8. So your pattern of 4, 2, 4, 2, 4, 2 is going to go until you stop, right? So we stopped at 4. Sometimes it stops at 2. Very rarely. But sometimes it stops at 2. So you just stop wherever it naturally stops. Okay, so you have 3 divided by 30 in the front, you have 0.1, and then you have 12.1 plus 4 times 10.4 plus 2 times 8.4 plus 4 times 6.2, 2 times 5.8, 4 times 5.3, 2 times 5.9. Watch what you're typing in. Yeah, this is where it gets a little sticky. If you don't punch it in correctly, you're not gonna have a very good answer. So I get 228.5, which is 22.85. Okay, so let's check. It says, the formula says if we double midpoint and add it to trapezoid, so 2 times 22.38 plus a trapezoid and divide by 3. Oops, sorry, what did I do? So, one more time, 2 times 22.38 plus 23.79 divided by 3, I get 22.85. Beautiful. My Simpson's rule is correct. Okay. All right. So this is your kind of a taste of how to use all 5 numerical integrations. So the numerical integrations are an estimate. There's going to be some error between the actual integral, the actual area versus what you are estimating it with. And we said the least accurate is going to be LRM RM, right? So then the error is going to be a lot bigger on the LRM RM versus like say a trapezoid or a Simpson's rule. So again, someone really, really smart realized how much error is allowed, right? So this I is your actual area. This I minus your estimation is the error that you have, right? So the area you have with LRAM, RM, MRAM, there are different levels of error. So what these error analysis help you figure out is if you are allowed a certain amount of error that's given to you and say, all right, well, I'm going to use MRAM and with an error bound of 0.05. So I'm okay with an error up to 0.05. Then how many rectangles must I use? At least how many rectangles must I use to get that kind of accuracy? Because we all know the best number of rectangles is infinite, but infinite rectangle is just a lot of work. And sometimes you really don't need that much, right? If you are okay with a certain number of errors, then you don't need infinitely many rectangles. You may just need a set number of rectangles. So, for example, if you already know the integral that you're looking at, so here's an integral, here's an area, and we say, okay, we want the error to be within 0.05, so within 5% of the actual area under the curve. Using an LRAM or an RRAM and using this formula, you will realize that, wow, I need about 300,000 rectangles to get that kind of accuracy. However, if you have the same integral, same area, same error, and you're using, let's say, a midpoint, even a midpoint, right? You will then see that, wow, I actually only need 600 rectangles. And then if you actually look at it using Simpson's rule, which we said would have the most accuracy, with Simpson's rule, you may only need 10 rectangles. So you see that the level of accuracy goes up drastically with each of these estimations. And so you need a lot less rectangles a lot less intervals under the curve to figure out your actual estimation in comparison to the actual area. Okay, so a few things to remind you is that K sub 1 is the biggest value that the first derivative can be on your interval. And typically it's your endpoints of your interval right here, A and B, right? K sub 2 is the second derivative and K sub 4 is the fourth derivative, okay? So again, rest assured we'll give you these error analysis formulas here, but let's see how you can work this out. So it says how many rectangles should be used in order to approximate this area within 0.001 error, so 0.1% error, which is really tiny, using the trapezoidal rule. Okay, so I want to use the trapezoidal rule. This is the one I want. All right, so I'm just going to write it again down here so I have a lot more access to it. So I minus T sub n, absolute value of it, K sub 2, B minus A cubed over 12n squared. So the error allowed here is 0.001. K sub 2, so I need to figure out the derivative. So I look at my original function here, 1 over x, so that's your original function, 1 over x, which is x to negative 1. I need a second derivative because it's K sub 2. So f prime is negative x to negative 2. F double prime is 2x to negative 3. So 2 over x cubed. Now I need to check by plugging in my intervals to see which one's a bigger value. So f double prime of 3 gives me 2 over 8. F double prime of 1 gives me 2 over 1. So 2 is definitely the bigger answer. That's my case of 2 number. Be careful when you're doing these because the error is an absolute value. So your case of 2, you're actually taking the absolute value of it. So if your two choices between -5 and -8, you choose -8 and you use the positive value of it. So you use that as your case of 2 or case of 1 value. All right, so just be careful of that. All right, I'm going to put 2 here for k. b minus a, so that's my interval. So 3 minus 1 cubed over 12n squared. So we're really looking for solving for n. N is the number of rectangles, right? So multiply the 12 over, so 0.012 n squared less than or equal to, you get 2 times 2 cubed, so 0.012 n squared less than or equal to 16, because 2 times 8 is 16. So n squared, and at this point you can just go ahead and set it equal to, because the absolute value is bounded, and so that less than or equal to is going to switch around, right? So it really doesn't matter. You're looking for an equal answer. So 16 over 0.012. So I have, oops, sorry. I'm just going to go ahead and check my answer. So I'm going to take the square root of 16 divided by 0.1012. And that will give me 36.5148. And you need to round up, because if you're under, you're not going to get enough rectangles to get what you want. So you always have to round up. Even if my answer is 36.01, you round up and get the next whole number, which is 37 rectangles. So 37 rectangles using a trapezoidal rule will give me enough accuracy so that it's within 0.1% of the actual integral, actual area under the curve. So kind of amazing.